Okay, so let me start out officially. So, good morning, students. This is a class of geotechnical engineering. So, we are discussing on module 2, part 2. So, till now we have discussed about permeability of soil. So, from last class, we have started CPS analysis. Okay, so in the last class we discussed about what is CPS, difference between CPS and permeability of soil, what is CPS pressure, and we have discussed Laplace equation of two-dimensional flow of water through a soil mass. Okay, and we have achieved a standard formula, or you can say relation, or you can say equation of Laplace equation. Okay, so equation for two-dimensional flow of water proposed by Laplace. And at the end of the last class, we have just introduced to the velocity potential. Okay, so if you remember the last class, so there is a new term we have discussed, that is phi. And what is phi? It is a multiplication of coefficient of permeability with total head loss, that is k into h. K into h is known as velocity potential, and it is denoted by phi. Okay, and the Laplace equation also represent the variation of phi with respect to direction. Okay, that is the variation of velocity potential with respect to direction. Okay, so we'll just continue from the last class. Okay, let me first share my screen. So I guess the screen is visible to you.
Yes, sir.
Okay, so here it is not that tough to understand, but it is little bit mathematical. Okay, so in the last class we have got this: phi is equal to k into h. Phi is equal to k into h, where k is your coefficient of permeability, h is your head difference, total head loss, you can say. So it is denoted by phi. And what is phi? Phi is representing your velocity potential. Okay, now there is another standard definition for velocity potential, and it is given here. So velocity potential may be defined as a scalar function of space and time such that its derivative with respect to any direction gives the fluid velocity in that direction. So that is, you can say this is a definition of velocity potential, or a significance of velocity potential. Okay, or you can say the importance of velocity potential. So as per this statement, we can say if you go for derivation, or if you can derive or differentiate, if you can differentiate this velocity potential with respect to x direction, okay, then the final result, that particular value, will give you the velocity of flow in x direction. Okay, and if you can differentiate velocity potential with respect to y direction, you will get fluid velocity or velocity component in y direction itself. So this particular statement can be proved mathematically by this. Here you can see. Now we know phi is equal to k into h. That is already we know in the last class. Now if we derive this velocity potential, that is phi, with respect to any direction, say with respect to x direction, so del phi by del x. If you do del phi by del x, what will happen? So just put the value of phi in place of here. So in place of phi, if you put k into h, k is a constant term, so it will come out. And finally, k into del h by del x will be remain here. And what is del h by del x? It is what? H represents your head difference. X represents the length traveled by the water. Okay. So del h by del x can be written as a hydraulic gradient in x direction, that is Ix. So k into Ix. Now as per Darcy's law, what do you know? K into I is equal to V. So since k into Ix is there, so we will get velocity in x direction, Vx. So we can connect this first and last result. Del phi by del x equal to Vx. Similarly, del phi by del y you will get Vy. So here from this we can say the differentiation of velocity potential with respect to any direction will give velocity or fluid velocity in that direction. If you derive del phi by del x, you will get Vx. If you derive del phi by del y, you will get Vy. Okay, I think it is under simple to understand. So this is all about velocity potential. Okay. Next, the another term is there, stream function. So we'll discuss about stream function. Okay, wait. If you can understand the velocity potential, it is also easy to understand the stream function also. Now it's look like similar, the definition. Stream function, it is also a mathematical term. Stream function, which is denoted by this symbol xi. Okay. Wait a second. Yeah. So by the definition of stream function, it is given as it is defined as the scalar function of space and time such that a partial derivative of this function means partial derivative of stream function with respect to a direction gives a velocity component in a direction positive 90-degree clockwise to the original direction. Okay, so it is look like similar, but there is a basic difference between stream function and velocity potential. In case of velocity potential, if you can derive phi with respect to any direction, you will get velocity component in that direction. But in the case of stream function, from here also you can find out, if you can derive stream function with respect to any direction, say del y, you will not get Vy, you will get Vx. Okay. Now if you derive stream function with respect to delta x, you will get Vy, not Vx, but with a negative symbol. Now why is negative symbol is given here? Because we have to consider the clockwise is positive. Okay, from this diagram, from this graph, you will let's understand this thing. So this is say x direction, this is y direction, it is known to you. Okay, now below this y, it will be minus y. Okay, and in the left side of x, it is your negative x. Okay, you can consider a plus symbol. Okay, so this is a positive y, below y it is a negative y. Here positive x, in this side negative x. Okay, now derive if you go for partial derivative of stream function, this is xi, with respect to y direction, in this direction, you will get a velocity component which is in a direction 90-degree away but in a clockwise direction, not in this direction, in this direction. Okay, so from y direction, from this direction 90-degree will be this way and this way, but you have to move clockwise, so we have to go in this direction, so we'll get vx. Since this direction represents what, x now, so you will get vx. That means if you derive del xi by del y, you will get vx. Similarly, if you can derive del xi, or if you can derive stream function with respect to x direction, you will get velocity component in 90-degree. That means you can get this direction or this direction. But this direction, it is, if you go in this direction, it will be anti-clock. We have to go clockwise. So this will be a clockwise direction. So you will get Vy. But in this direction, this zone is for negative. So you will get minus symbol here. So we can replace this minus symbol in this direction. So we'll get del xi by del x equal to minus Vy. So here this negative symbol come like this. Okay, so after getting this equation, till now we have got four equation or four relation of stream function and velocity potential, and comparing all these four equation, we can find this general equation, that is del phi by del x equal to del xi by del y, and del phi by del y equal to minus del xi by del x. Okay, you have to remember this. Okay, if you can understand velocity potential and stream function, you no need to remember this. If you can understand, you can automatically find out this particular formula. It is not kind of formula, it's just a relation. It is a relation between velocity potential and stream function. Okay, so these two equations are also known as Cauchy-Riemann equation. So in some exam may ask you that define Cauchy-Riemann equation like that. Okay, so that is, it defined the relation between velocity potential and, and stream function, Cauchy-Riemann equation. Okay, so after this let's discuss about flow net. I want to go back to that previous slide, a previous screenshot here. So this velocity potential and stream functions, are both derived by the Laplace. Okay, and they are the solution of Laplace equation. Okay, and these two can be represented graphically, in the form of streamline and equipotential line. Okay, so here you can see some some drawings are showing here. They are theoretical line or imaginary line. You cannot see, for only to study the seepage of water under pressure, you can use the help of flow net. Okay, and what is flow net? Flow net is a combination of, or is a representation of, equipotential line and streamlines. Okay, and lying mutually perpendicular to each other. and these lines are mutually perpendicular. Okay. Now here, if water is flowing in this direction, suppose you are considering water is flowing from left to right, from here to here, okay, and it is shown by this delta q, okay, it is the unit discharge, that means discharge per unit time. Okay, so along the flow line, okay, along the flow of the water, the line drawn parallel to the flow line, or flow of water, they are known as streamline or flow line. Okay, they are along the flow of water. So water is flowing in this direction, so the line drawn parallel to the direction, it is, they are known as streamline or flow line. And the lines which are drawn mutually perpendicular to the streamline or flow line, or you can say mutually perpendicular to the direction of the flow, they are known as equipotential line. Okay, equipotential line. Why they are known as equipotential line? Because I want to make it very easy. Suppose I told you the water is flowing in this direction from left to right. Okay, that means there must be some hydraulic gradient. This somewhere water is coming from this point and going to this point. That means that point and that these points are between these 2 points. Some head drop will be there. Suppose water tank is there having height 10 meter. Okay, and here in this side water tank is there having height 5 meter, and let's say connect these two water tank. Okay, I'm giving you just very simple example. Then what will happen? Water flow from this tank to this tank, or from higher to lower? So it is obvious the water will flow from higher to lower. And between these two tanks, what is the head difference? That is what? 10 minus 5. That is 5 meter. Because of this 5 meter head difference, the water flow from higher elevation to lower elevation. This is create the hydraulic gradient h by L. Okay, that particular h, that is 5 meter for that particular example, can be divided in equal portion. Okay, let's say the total head difference is 9 meter. Okay, let's say total head is 9 meter. That means this particular point is 9 meter higher than this point. Okay, now make some intermediate line, these two intermediate line, in such a way that the head difference become constant at this tree zone. If you create these two line, tree zone is created, isn't it? The total head difference between this point and this point is say 9 meter. Then this point will be at say difference between at 3 meter. Okay, and the head difference between this point and this point is also 3 meter, and head difference between this point and this point also 3 meter. Okay, so 3 meter head difference here also, 3 meter head difference here also, and 3 meter head difference is here also. The total head difference 3 plus 3 plus 3, how much? 9. So so this line are created or drawn in such a way that the potential drop between the lines become equal or constant. That's why they are known as equipotential line. That means the head difference between this point and this point will be equal. Okay, the head difference between the point will be equal. Fine, and this as a whole, all these thing or this diagram is known as flow rate. Okay, the equipotential lines represents contours of equal head or equal potential. Okay, And the direction of CPS is always perpendicular to the equipotential line. That means this is a direction of CPS. Water is flowing in this direction. You can say water is seeping in this direction, and equipotential lines are perpendicular to the direction of the seepage. So you can say in a reverse direction that direction of seepage is always perpendicular to the equipotential line. It's a very key statement. You have to understand this. Now, by the definition of streamline, a streamlines it represents what? A path along which the individual water particles sip through the soil are called streamline or flow line. So water flowing in this direction, so this line represents the flow direction. The path along which the individual water particles sip through the soil are called streamline or flow line. I again want to tell you that this is a imaginary line. This is an imaginary line which can be drawn within a structure, say for example within a dam. Okay, to study the seepage of water. Okay, how water will go through and what the flow path the water can take through the dam structure or cross-sectional dam structure. We can study. We can study using this particular concept of flow net. Okay, fine. So let's discuss some property of flow net. There are some property of flow net that let's discuss about flow net. Okay, so properties of flow net here it is given. The first one is what? The flow lines and equipotential lines meet at right angles to one another. That is already discussed. They are look like a square net. Okay, so flow lines and equipotential lines are meet. The lines meet at right angles to one another. Next, number two, the fields are approximately square so that a circle can be drawn touching all the four sides of the square. Now, what did this mean? Okay, I have to go back to that diagram. So you can concentrate here this diagram. This shaded portion is actually represent field. These all are field. Okay, these all square box surrounded by two equipotential line and two streamline are known as field. Okay, and this field are approximately square such that you can draw a circle within the field touching all four sides. Okay, you can draw a circle here. This is a property of flow net. Okay, next, the quantity of water flowing through each flow channel is the same. Similarly, same potential drops occurs. Similarly, same potential drop occur between two successive equipotential line. Now, first of all, what is called the discharge is same through each flow channel. Now, what is flow channel? This represents flow channel. Okay, here some definition also given. Flow channel: the portion enclosed between two successive equipotential lines and successive flow lines is known as field. That is already discussed. Okay, this is called field, and the portion between any two successive flow lines is known as flow channel. Flow lines means this one is a flow line, this is a flow line, and the portion enclosed between these two flow line it is known as flow channel. This is one flow channel, this is second flow channel, this is third flow channel. Okay, and water flowing through in this channel. Okay, and as per the property of flow net, the amount of water flowing through each channel is same. That is, if del q amount of water is flowing through this, the same amount of water is flowing through this channel at this channel also. Okay, and also the potential drop is same between the successive equipotential line. It is, of course, it is a property of equipotential line. The head drop delta H head drop here is similar to here as well as here. This is as per the property of flow net. Next, smaller the dimension of the field, greater will be the hydraulic gradient and velocity of flow through it. That means if uh, this particular field size gets smaller, okay, then the discharge will be higher. Okay, it is very basic thing. So if you if sorry, not discharge, velocity will higher. If you reduce the cross sectional area, you can say, since water is flowing in this direction, if you reduce the area to maintain the constant del q, the velocity will increase. Okay, smaller the dimension of the field, greater will be the hydraulic gradient and velocity of flow through it. Okay, so this is all about the property of flow net. Okay, so this is all about today class. Next class we'll discuss about application of flow net. Okay, we'll discuss about application of flow net. Mainly this flow net is used to find out or to determine the amount of water seep through a particular structure. How much water can seep through a particular dam structure, we can find out, okay, using a flow net. How? We'll study in next coming class. Okay, for today it's too much for you. Just go through the notes, I will share it. So yeah, so I'll just stop my sharing here. Okay, we are also going to do one problem based on CPS analysis using flownet. Okay, how to find out the charge. There is a very important formula which also come in competitive exam. Okay, it's very important chapter or topic, that is flownet. Okay, we haven't done problem related to index property. We're going to do, okay, after completion of the syllabus we'll do some problem on that also. That means I'm talking about the first chapter. Okay, okay then. So let me first take the attendance now. Today is 22, no? Okay, do respond. Okay.